We're now going to look at energy diagrams for two interacting point charges. And I'm calling it plotting because what's really important here, in addition to just the fact that it's an energy diagram, is also plotting what the potential is going to look like. So let's first look at like charges, and we're going to consider these to both be positive. We have a before scenario and an after scenario. And in this case, we're starting them some distance apart with a speed towards each other. And for simplicity, we're going to assume that they have the same speed. So keep in mind that we need to talk about the energy of our system. So that's going to be the total potential energy of our system, and then the kinetic energy of each of them. Our final scenario is the closest approach. That means velocity is equal to 0. So on our energy diagram here, note that we're plotting R. So we're not actually plotting the position of one or the position of both of them. We're plotting the distance between them. And so our closest approach, note that we have 0 here, is here. Notice it literally relates to our picture. This is a nice way to do it. And at that point, our kinetic energy is 0. And so that's where our mechanical energy, labeled here, is equal to our potential energy. Our potential energy has the form of 1 over U with some constants. Sorry, 1 over R, right? So this is a form of 1 over R with some constants due to Q and both Q's and 1 over 4 pi epsilon naught. But so you see that as they get farther apart, our potential energy decreases and then our kinetic energy increases. So if this is our Ri, our initial distance, then this was the initial kinetic energy, keeping in mind that they both actually had a velocity. So that's how to plot this. Again, we have positive potential energy here because we've said, again, thinking about 1 over R, over here at R equals infinity, I'm going to plot that like this. That's where potential energy finally becomes 0. But that's actually at infinity. So that's not too hard. Now let's think about opposite charges. Now we're actually going to start them close, our initial here, but with velocities that are going away from one another. But these are oppositely charged, so they're going to have an attractive force that's going to slow them down, and they actually have a maximum separation. At this maximum separation, they stop, and they're going to start accelerating towards each other once again. So note that our potential energy is always negative, right? So note we have 0 potential energy here, and again over here at R equals 0, we're going to have that be the place where potential energy is finally equal to 0. Over here at R equals infinity. Over here, potential energy is always negative. So when we start them at some position, we have a certain amount of mechanical energy, which is also negative. Look at that. So notice that mechanical energy is always going to be negative for opposite charges, and if they're bound. And what that means is that they would actually stop. So that's something a little bit tricky to think through. So our mechanical energy is negative, and so we start with some amount of kinetic energy and some amount of potential energy. They get further and further and further and further and further away until they hit those two lines, and that corresponds to kinetic energy becoming 0. That's where they're stopping, and then they turn around and come back down, right? So imagine them rolling down this hill. They're actually going to have infinite kinetic energy when they're right on top of one another. And at that point, they also have infinitely negative potential energy, right? Again, this is 1 over R. What happens as you take R to be 0? Well, this blows up. So we really can't define the energy of 2 point charges that are exactly in the same position. That's why we can't set potential to be 0 there. That doesn't make any sense. So we have to set potential to be 0 at infinity. And so for oppositely charged particles, we actually deal with negative energies. That's okay. Remember that we're always just talking about changes in kinetic and changes in potential energy, which is why this makes sense.